Hi Tim, you're looking particularly snazzy today. What are you wearing?
I'm wearing a piece from a company called Grace and Garbo, and actually, you know a little bit more about them than I do, to be honest.
Yeah, you're right, I do. And
You're
as
the
you can see,
fashion queen, yeah.
I'm also wearing a piece from Grace and Garbo. So this is a delightful knitwear outfit set up in Birmingham. What they do is they source knitwear, quality knitwear from all around the world. So it's vintage, one-off pieces, many of which they then hand embellish, like the one you're wearing today with its beautiful purple flowers. And so they're big on sustainability. Nothing goes to waste. Everything is sort of recycled and reused. And if you want to know more about them, then have a look at the link beneath this episode.
And thank you very much to them for supporting our podcast. Hope their sales soar.
Yeah, thanks a lot, Grace and Garbo.
Well, thank you very much, Professor Lee Smolin, for joining us on our podcast today. It's a real honor to have you as kind of one of the deepest thinkers in theoretical physics.
That's very flattering. Thank you.
Syma, do you want to sort of kick off? You actually studied a bit of quantum mechanics at university a while ago, so why don't you start with some questions?
Yeah, well, I was wondering if obviously, so when I was an undergraduate, we studied quantum mechanics, we studied classical mechanics, and we studied them as I guess almost as complete theories. But I was wondering if you could give us a bit of an overview of, in your eyes, the perhaps the limitation of quantum mechanics for our listeners, and why, before this recording we discussed that you think it is an incomplete theory and why that might be the case.
Very good. So quantum mechanics is a theory that was invented in Central Europe sometime around 1926, 1927. And it met a confused reaction to the mainly European scientists that worked on it. So there's a beautiful history of quantum mechanics as a scientific revolution, which started in about 1913, 1911, and culminated in the birth of the theory in 1926, 1927. But many of its founders were very unhappy with it. And they had good reason. It broke with a number of the important principles that people thought a physical theory should live up to. It is not deterministic. It's not local.
Was that the reason they were unhappy with it? Because of the lack of determinism or the lack of non-locality or the lack of locality?
For some people were very unhappy with those.
And
Other people say Einstein, and people who are more like him in scientific temperament were unhappy about the fact that it didn't provide a realistic version of nature. It didn't give you a picture of nature.
I guess it kind of changed, it sounds like a very glib thing to say, but it changed everything, right? It changed the way we think about the world around us in a way that I guess might have seemed nebulous at the time. Is that right?
As people started to think about it, they realized that it didn't give a picture of nature. And it gave a very formal connection to the natural world that was broken into two pieces. And it's very odd that a scientific theory acts differently on different kinds of things. But quantum mechanics did. You have to divide the world into two parts and attack part one with, we'll call it rule one, and attack part two with rule two. And
those two parts are the small, the micro, and the larger. Is that right? The macro?
No, that's no longer right. That the founders got away with that for a while, but you can't certainly say it now. Part one, or rule one, says that the theory describes a wave that moves in not space-time, but phase space. And this wave propagates, and that's all that happens in rule 1. It propagates linearly and just goes on propagating no matter what happens. Rule 2 says that when you're describing an experiment where a definite answer is required, then it jumps, and it jumps when you say that you're making the observation, and it collapses, we say, so that the wave collapses to a point, which is the point that we can say the particle was seen or observed. And then the description is a jump from the phase space to the point that the theory is identifying as the position of the particle.
So the rule 2 one is the probabilistic one, right? Is that right?
Yes.
We cannot know for sure, but there's a high probability that something is in a certain place, and just by the act of observing it, we may perturb that. Did I understand that correct?
Yes, well, you understand as well as anybody. That's hard to imagine that that's correct, but that's what the theory says.
So do we know why particles need waves or have waves, and why waves are also particles? I mean, is that the bit we haven't really answered? We know that there is this wave particle duality, but we don't really know why.
Well, let's go through the different attempts to answer your question. So one position was held by Louis de Broglie and promulgated by him. He was a French aristocrat, and he said that the wave propagates. It propagates the probability, and what happens when people say rule 2 is coming in. Rule 1 is just the propagation of the probabilities, and rule 2 is when they jump to a new position, which is based on the choice that you ask for. That is, you can ask for, what is my momentum at this time? And it will tell you a definite momentum. Or you can ask for, what is my position at this time? And it will tell you a definite position. But it's not, that's all it will do, and it won't tell you the position and the momentum at the same time. That's what's called the uncertainty principle, Heisenberg's uncertainty principle. And Heisenberg saw that as the probabilistic description is the propagation of the wave. And there is both, according to de Broglie, a wave and a particle. Both exist. And the particle jumps according to the probability distribution given it by the wave. So that's a rather dramatic difference from any physics that there had been before. But that works very well. When you make the connection between the wave and the particle, when you just posit that the wave is a wave of probability that will determine where the particle jumps to when you ask it to jump.
So if I've understood this correctly, so I'm trying to process what you've said, and also my background undergraduate notes are coming back to me. So when we're at these tiny subatomic sort of scales, and then we're dealing with this issue, then this, I guess, the manifestation of the wave particle duality becomes really important. But then when we're at this sort of middle macro scale, when we're dealing with, for example, a bouncing ball on the ground, I don't have to be able to describe and model that. I don't have to worry about the wave particle duality. I can have just my particles. Is that correct?
There is a limit of the theory in which the particles are kind of just particles which bounce according to a probability distribution. But it's no longer the case that you can claim for this that the division is the very large versus the very small, because your colleagues are able to now photograph the whole thing. You can make waves that travel and you can see the waves, I believe. They're as large as I'm trying to say the best way to say it, but the only way to say it is really that in modern chemistry, you can see the particles jump.
Right. Okay. So even at those macro scales, we have a quantization. Is that what we're saying? We have discrete jumps rather than a continuous.
Yes.
Okay. So I think that's something that has changed from when I was an undergraduate. We were sort of, so this is this is new. Well, new in that I'm pretty old, so it's not that new, I guess.
Well, you don't look so old that I'm really sure.
So I guess the other kind of big bit of theory is at the other end. So it's Einstein's theory of relativity, and one of the challenges that physicists have at the moment is that that Einstein's theory of relativity, which describes what happens on much larger scales and deals with gravity and deals with light and time, that doesn't link well to quantum mechanics. Is that correct?
It's difficult but not impossible to make a quantum theory of the equations of general relativity. And then you have a kind of space of waves of possible choices of initial data that lead to infinite numbers of choices you can make for the wave propagating. Because now you're in a domain where there are fields, and fields are the things that are dynamical,
Mm.
that move along and that have the analog of the Newton's equations applied to them.
And so, which of the theories that are out there? So, I think there's things like quantum loop gravity, which you've worked on, and string theory, and various other theories that have been proposed to link together, well, create a theory of quantum gravity that allows Einstein's theory of relativity to link to quantum mechanics. Which one of those is most promising and most empirically testable? Which one of those theories do you currently favor?
They're both infinitely testable, but so far have not been tested. Also, I want to say that they're very different spirits, string theory and loop quantum gravity. Loop quantum gravity follows a set of rules to construct from a classical theory of quantum theory. And what it takes from the classical theory is the notion that the configuration of the gravitational field is changing in time. And it's very beautiful because you get to choose which time you use, what you get to choose what clock is. But it's a very conservative theory. There's very little choice in it. You start with a version of the configuration space, which is described by some loops in the space-time, which carry things around. That is, rather than saying, where is this piece of space-time and where is that piece of space-time, and then trying to put the whole thing together, what you actually are trying to do is take a point in the configuration space and describe it in a different way. We describe it in terms of probabilities for loops. And so what we're seeing, if we imagine we're looking into a quantum gravity experiment, is a configuration of loops which are moving around each other, and there are an infinite number of those loops. And we absolutely follow the rules. We don't cheat anywhere. It's a very disciplined approach. And we get out of it a visual picture in terms of, well, imagine you can think of the loops as classical, and the theory gives you a description of how each loop is moving in space. That's very bad, sure, but let's go with that.
How can we test it then? What and so why you say they're both infinitely testable, but why haven't I like my experiment. I like to be able to do experiments to separate theories and to
Sure,
separate hypotheses.
sure. Take a magnetic field, and a magnetic field is in a certain kind of state, which is called a superconducting state, divides up into loops, which carry each loop carries a certain amount of flux, which is magnetic flux. And there's a rule for how to put them together, and a rule for what changes as you go forward in time. In loop quantum gravity, you have fluxes, but the fluxes are basically fluxes of the area of the gravitational field. So the gravitational field describes geometry in a region, and if you draw a lot of loops to make approximate pictures of that spatial geometry, then that's the things that the equations of gravity act on. And you're asking the theory to, you're asking the theory to tell you what the probability is for the loops to go in different directions, to intersect each other, and so forth. So, and it becomes very discrete. So there's a picture of nature where the world is filled with these loops and dual loops, which are like the electric field dual to the magnetic field. And this whole thing is sort of writhing in time as time goes on. Now, indeed, this is all happening down at the Planck scale. And how do you test it? So there's a very indirect line which leads to a hypothesis related to this whole story, which is the cosmological natural selection. But you're not actually testing loop quantum gravity in that picture. You're testing the theory of cosmological natural selection. And I can tell you how we do that and how that relates to experiments. That's not directly related to loop quantum gravity.
So perhaps let's move on to just so our listeners have an idea then about cosmological natural selection, because that's I think a nice
Sure.
nice
It's a
segue.
cool story. Yes.
So my understanding that is that under cosmological, so in biology, in the field that I work in, there's organisms are competing against one another, and sometimes cooperating, but they have fitness, and the fittest ones tend to win out. And in cosmological natural selection, if I understand it, there are potentially multiple universes that are competing against one another, and fitness is the propensity to produce black holes, if
Right.
right. And one universe links to another through black holes. Is that correct? Where if you were the universe, another side of a black hole might have slightly different parameters, slightly different strengths of gravities of each of the forces. And is that I've probably murdered your beautiful theory there, Lee. And apologies if I've done that. But
Only a little bit. Only a little bit.
okay, let me let you talk then.
Let me start by saying what the problems were that I was trying to address with this theory. So there's what's called a standard model of particle physics, which describes which elementary particles exist, what their properties are, and has a large number of parameters to fix all those things that we observe and don't understand. And it's an embarrassingly large list of things that we observe and don't understand. They include the masses of all the fundamental particles, which have which charges, some parameters associated with kind of the twisting of the magnetic fields of the space times that everybody is moving in. And any test of this is going to be indirect, but let me indicate why and what's at stake here. What's at stake is the very idea that the laws of nature are fixed. And I think that as an elementary particle physicist, which is how I was trained, I began to get very disturbed in my college and graduate school years about the fact that there was about 20 parameters that you needed to set, that there was no explanation for, that cashed out to the particles, the masses and the charges of the fundamental particles. And one of the things I was very unhappy about, but then I got to be very happy about it, is just the idea that the world, when we look at it, is like some biological something, some organism. And as the world evolves, these parameters change in time. And the change happens through the production of black holes. So we want to see a black hole as something like a parent, which gives rise to a number of parents. And the distribution of new parents is random on the initial one. And you imagine that you look in the sky, and if we could see really well, and not the crummy way we can see now, we would see lots and lots of black holes being born. And we know a lot about that, how black holes are born in supernovas, which is the site of black hole production, and how the supernovas give rise to explosions, or are themselves explosions that give rise to different masses of stars. And some of them are very low mass. And in fact, if they're below 2.0 solar masses, they will have a part that collapses to a black hole. And then the question is, what happens to the black holes? And this is the very low range of black holes that the universe will produce. But there's a distribution in how we make the black holes and the properties of the star that turn into a supernova that collapsed and made a black hole. And now you can ask, are there any properties that make a supernova collapse not to a neutron star, but make to a black hole? And it turns out that the mass of this remnant is what's determinant. So above this mass of 1.9 solar masses, all the remnants are going to break into black holes, and will then expand into very light black holes. And so there we're looking at the creation process of stars and black holes. And the distribution is variable and is changing as time goes on. So you have a very dynamic and evolutionary picture of how the distributions of different stars is growing. And you have a choice here, just psychologically, of either giving way to the biological metaphor and taking it up, or resisting it. I don't know what you want to do, but
well, we've got to. You can't resist it, as I'm a biologist. That would be wrong.
Okay, so
can I just ask, Lee, are you just something you said right at the start? So are you saying that our at the moment we're limited by what we can see. And that's providing an impediment to our sort of us resolving some of the issues between these theories is just our inability, just with our instrumentation, etc., just to see.
No, not so much. We can really see and count the stars of different masses as they're formed. There
Okay.
is an initial mass function, which is the distribution of stars of different masses just at the point when they're formed. And we know that that decreases something like the mass to the to the minus 1.7, which if you have done that kind of biology, star formation, you'll be familiar with the initial mass function. And what I'm telling you is that the initial mass function is determined here. It fits the metaphor, and with a particular 1 point minus 1.7 distribution, and that's very close to the one that's used in biology that nature uses.
Yeah.
Then you can talk now about dinosaurs and so forth, but there's an initial mass function for what's dinosaur and so forth. So this is great stuff. I mean, I didn't know much biology and any astronomy when I discovered this and discovered how simple an explanation this was. And I started calling up people I knew who knew this stuff better than me and learning how to use it to be predictive.
And so the evidence at the moment that's been collected by the sound of it still suggests, is supportive of cosmological natural selection.
Yes, the standard distribution of black hole masses now is about 2 or 1.8 to 1.222. And people are working hard to, well, that's the low branch of black holes when they're first born. What there's not so much in biology is very massive, very massive black holes, which can't be explained by the same story, but there must be some other story that explains them. And people are looking for that.
So I guess the last question, is we're running out of time now, is, but what do you see what do you expect the sort of next big breakthroughs to be in particle physics or in, quantum loop gravity or string theory or even cosmological natural selection? What are you
looking forward to? Yes, well, first, in cosmological natural selection, we need to understand more of the different parts of the ensemble. And that goes to understanding things like star formation. And that I expect, there are a number of papers out the last year or two, which refine the assumptions and look at different parts of the process that makes black holes. So there's a lot of good astrophysics to do.
And what for you would be the biggest, like personally, on a personal level, if you could have sort of one big breakthrough that you want to see happen next, what would that be?
It's quantum gravity. And I've made the group of us together who are connected to loop quantum gravity have been refining it and making it work much more coherently, much better. And some of those are using different mathematical tools. I'm using some mathematical tools which are actually close to string theory. And so I have a kind of well, something that you might call an evolutionary version of string theory. I have a string theories that evolve through processes very much like how trees evolve. Or
So, Lee, just at a very
sure,
fundamental level, I just wanted to explain one thing for our listeners who may not be, who likely are not, familiar with the concept of loop quantum gravity. I just wanted to just check that. So if we have this view, according to Einstein, of general relativity, where we have this concept of space-time, again, for our listeners who might not be familiar with the concept of space-time, it's essentially a mathematical way of sort of combining geometry and time. So we have sort of 3 dimensions and time when we put it all together. So we have these 4 dimensions. If in the general relativity formalism, then that is like a continuous bit of fabric, if we like. But in loop quantum gravity, what we're seeing is at the sort of very tiny level scales, we see the world rather, or this space-time rather, as sort of connected loops that are made up of lots and lots of loops everywhere, which are all connected, and that's the fundamental sort of building block. Would that be a fair way to describe it?
yes, and there are lots of people working on that, the details of that, and they're coming up with some very interesting pictures. I don't believe there's a continuum anywhere in the correct picture. So I have a different picture
Sure.
in which I construct space-time
Yeah.
through a set of rules which never gets denser than a certain amount. And a certain amount is like a Planck amount, so it's a huge density. But I don't need to, I don't have continua down at the smallest scale. It's working remarkably well at this point.
We've taken up a lot of your time. I really appreciate you taking the time to talk to us. It's been absolutely fascinating, and good luck with the continuing research. I mean, we'll look forward to hearing those breakthroughs. And thank you.
Very
Yeah.
much.
Thanks a lot, Lee.
Bye for now.
Yeah. Bye bye.